All right, so this is a practice problem using the work energy theorem, and it tells us that a car comes to a stop in 25 meters, and the car has a mass of 1,500 kilograms. It was moving at 35 meters per second, so how big of a force did it experience in coming to a stop? All right, my markers are on the other side of the screen, so hold up. Okay, so if we look at this in terms of the work energy theorem, we could, again, do kinematics and do a force analysis and take up a lot of space. I know you're all experts at that, but let's now look at it using work energy. All right, so we want to remember that the network acting on an object is equal to its change in kinetic energy. And because we know that this car was moving and then it came to a stop, we do know that it had a change in kinetic energy, one that we can figure out. So that change in kinetic energy, remember, is the final kinetic energy minus the initial kinetic energy. And so we have 1/2 the mass times the final velocity or speed squared minus 1/2 the mass times the initial speed squared. We do know that the car comes to a stop, so this speed goes away. Our final kinetic energy is 0. And so we have the change in kinetic energy is minus 1/2 the mass times the initial speed squared. All right, so if we take that and we use the information that we have 1/2 the mass of the car is 1,500 times the initial speed of 35 meters per second squared. And we determine what our kinetic energy change, oops, I left a negative sign out there, which is important because the force is going to be working against the motion, against the direction. So we have 0.5 times 1,500, oops, my calculator's off, 0.5 times 1,500 times 35 squared. I am hitting the wrong buttons. All right, and we get a change in kinetic energy and also equal to our initial kinetic energy of negative 918,750 joules. And of course, we have way too many significant digits there, but we're not done with the problem just yet. So that is our change in kinetic energy, which we know is equal to the net work. Now we also want to remember that the net work is equal to that net force times the distance in the direction of the force in the direction of the displacement. And so if our net work is minus 918,750, our force, and we know that we stop in 25 meters, we can determine the force acting on that object. And we get 37,000 newtons of force in the negative direction as I've described it, moving to the right and coming to the stop. So again, much faster process, relying on the power of work and energy, no pun intended. And that negative should make sense because the force is acting to slow the object down, and if it's moving to the right and slowing down, it has to have a negative acceleration and therefore a negative force. All right, good job.